Hello everyone. In this video lecture, let us continue understanding Module 1 Hierarchical Modeling Concepts. In this lecture, let us understand what is a module, what is a module instance, and the various levels of abstraction. A module is the most basic building block in Verilog. So a module, it can be either a single element or it can be a collection of lower level design blocks. Module basically provides all the necessary functionality to the higher level blocks through the input and output interfaces. The best part of a module is that the designer can modify the internals of a module without affecting the rest of the design. Let us understand the module and how it is declared in Verilog. So a module is declared using the keyword and it ends with the keyword end module. Each module we declare must have a module name, which is an identifier or a user-defined name for the given module. The rules for writing an identifier or a user-defined name is that the identifier must and should begin with an alphabet or an underscore. It can contain numbers, and the only special character allowed other than the underscore is the dollar symbol, but it should not begin with a dollar symbol. These are the rules to write an identifier in Verilog. Other than the module name, the module terminal list is also important in a module, which describes the list of input and output terminals of the given module. So now let us observe the syntax of writing a module. So basically we write module followed by the module name, which is user defined, followed by the module terminal list, which is the list of the input and output variables in the given design, which is written within parentheses, and the first line of code must and should end with a semicolon. After the module is declared, we have the various declarations and statements, which is represented here as the internals, the module internals. Let us not get into understanding the module internals here. Every module which has begun must end with the keyword end module. Now let us see an example of a module description of a T flip-flop. Consider the T flip-flop module given here. The name of the module is T_FF T flip-flop. Identify the inputs and outputs of this system. So this system has clock signal as the input signal, reset as the input signal, and Q as the output signal. Let us name this module as T_FF, that is T flip-flop. So module followed by the module name followed by the module terminal list, the list of input and output terminals. So if we observe, the first line of code would be module, which is the keyword, followed by the module name. We are referring here to the module name as T_FF T flip-flop, and within parentheses we list out the input and the output terminal list of that particular module and end it with a semicolon. Later we have described the functionality of T flip-flop in the internals of the module, and we know that every module must end with the keyword end module. Now, the internals of the module can be written at various levels of abstraction. Verilog supports 4 levels of abstraction, namely the behavioral or the algorithmic level, the data flow level, the gate level, and the switch level. So these are the 4 basic levels of abstraction that we can write the internals of a module. So module behaves identically irrespective of whichever abstraction. So if a module is described in behavioral or in data flow or in gate or in switch, the module behaves identically in any level of abstraction. The internals of the module are hidden from the environment. So irrespective of the abstraction levels, the module works perfectly according to the functionality. Let us look into each of these levels of abstraction with a simple example of each. The first level of abstraction is the behavioral description. So the behavioral description is the highest level of abstraction provided in Verilog. So designing at the behavioral description is similar to C programming. When we write a behavioral description, we need not worry about the hardware implementation, as this is the highest level of abstraction. We do not worry about the technology or the hardware implementation details. So in a behavioral description, we mainly describe the behavior of the system irrespective of the hardware implementation. So this is a sample code of a half adder written in behavioral description. Let us not get into the understanding of this code, but we can observe here nowhere in the code we have mentioned about any of the hardware requirements like the gates used. It is a pure if-else statement, which is a conversion of the truth table. So here if you observe, x and y are the inputs, S and C are the outputs, that is sum and carry. We can declare the input and output in the module line itself. So we are checking according to the truth table. We know if inputs x and y are 0, 0, sum is 0, carry is 0. If the inputs x and y are 1 and 1, the sum is 0, carry is 1. Else, if any one of the input is high, the sum is 1 and carry is 0. So this is a pure behavioral description where we do not worry about the hardware implementation. So this code is written in accordance with the truth table of a half adder. The second level of abstraction is the data flow description. So the module is designed by specifying the data flow, how data flows from the input to the output through various operations. So how the data flows from the input to the output through data hardware registers and how the data is processed. We write the same half adder code that we had discussed using the certain operations or Boolean equations. So mainly data flow description, we use Boolean expressions to write codes, and the keyword assign is used to highlight data flow description. To obtain the code, we need to simplify the truth table and get suitable expressions. So the same half adder code written in behavioral description, written in data flow description looks more simpler in terms of Boolean expression of the output variables. So we have obtained sum is equal to A XOR B and carry is equal to A and B. Using the keyword assign, we say assign S is equal to A XOR B. We will be understanding each of these operators, the declarations, in detail in the further modules. The third level of abstraction is the gate level description. So as the name suggests, in gate level description, we implement the module in terms of the logic gates and the interconnection between these gates. So designing at the gate level description is similar to designing at the gate level logic diagram. So the same half adder example which we have designed, we have obtained the gate level logic diagram of a half adder, which is made up of one XOR gate and an AND gate. In a gate level description, we just call the instantiations of these gate primitives which are already predefined. Gate primitives are nothing but gates which are already defined, their functions are already defined. We just need to call them in the program and pass the parameters in the order of output comma input. So in this XOR gate, the output variable is sum and the input variables are A and B. So they have to be passed in the same order, because in the predefined gate primitive, output variable is included first in the terminal list. So we have to follow the order output comma input. Last level of abstraction, which is the lowest level of abstraction, is the switch level description. In switch level description, as the name suggests, switch is a transistor. This is the lowest level of abstraction, and here we can implement a module in terms of switches, the storage nodes and interconnection. So basically we try to design here at the transistor level, and if we are writing a program in the switch level, it is important to have knowledge of switch level details. That is, we need to have idea about the transistor connections of the hardware schematic. So this is an inverter circuit. This is the CMOS version of an inverter. This represents the code where you call the individual NMOS and PMOS transistor to write a gate level description. So let us not worry about the logic of the code because we will be studying each of these descriptions in the further modules. So a summary about the levels of abstractions. We can mix and match any of the 4 levels of abstraction. So RTL, that is the register transfer level, is a description which combines data flow and behavioral description to make it suitable for synthesis tools. If we are writing a design with 4 modules, Verilog allows all the 4 modules to be written at different levels of abstraction. The higher the level of abstraction, the more independent it is from a technology. Lower the level of abstraction, it is completely technology dependent and it is less flexible when compared to the higher level of abstraction. The best example is the C and assembly. C being higher level description is more flexible when compared to assembly, which is a lower level description and which is less flexible. Now, let us understand what is an instance and what is the difference between a module and a module instance. A module basically provides a template from which we can create the actual objects. So it gives us a framework from which we can create any number of the objects required. So when a module is invoked, instantiated or called, Verilog will create a unique object from the original template, that is the original module. Each object which is created will have its own name, it will have its own variables, own set of parameters and the input-output interface also. The process of creating objects from a module template is called instantiation. So the process where we invoke a module is called as instantiation and the object that is getting created is called as instances. So the process of creating object is instantiation and the object itself is an instance. We shall understand this with a better example. So in the top level block that we wrote for ripple counter, the top level block would create 4 instances from the T flip-flop. Each T flip-flop is instantiating or invoking a D flip-flop and an inverter gate. So this can be better understood with an. Let us understand instances with an example now. Consider the ripple carry counter, which is the top level module. This ripple carry counter, which is built using 4 negative edge triggered T flip-flops, instantiates or invokes these 4 instances, copies of the T flip-flops. So first we define the top level module, which is the ripple counter, which instantiates 4 T flip-flops internally. So let's do the module declaration. So we know we have to declare a module using the keyword module followed by the module name ripple counter, list out the output and input variables. So when we see outside this dotted line, which is the ripple carry counter module, we have 4 outputs Q0, Q1, Q2, Q3 and we have 2 inputs clock and reset, which are listed here. The terminal list listed here has to be declared as output and input variables. Now we start instantiating the T flip-flops. So we instantiate the T flip-flop module with its name. So we are instantiating T flip-flop as T underscore FF. We give a name to it, instance name, and the order in which we write these variables depends on the order in which we write the actual T flip-flop module. So assuming that we are going to list the output variable first, go to each T flip-flop, observe the output variable. We are going to write output variables, input variables. So for the first T flip-flop, we have Q0 as the output, clock and reset as the input. Similarly, for the second T flip-flop, we have Q1 as the output, Q0 and reset as the input. For the third flip-flop, we have Q2 as the output, Q1 and reset as the input. Similarly, for the fourth T flip-flop, we have Q3 as the output and Q2 and reset as the inputs. Finally, the module is ended using the keyword end module. Now, we are going to define this T flip-flop module. The T flip-flop now becomes the sub-block. So, we are going to define a T flip-flop which is going to instantiate again another D flip-flop and an inverter. So, module, the name of the module should be same as this module which is instantiated here. So, T underscore FF. We are listing out the output variable first because we are passing output parameters here. So q comma clock comma reset. Then we declare the output variables. We declare the wire and input. Why are we declaring the wire? Because we find an intermediate output here, which is the output of the NOT gate. So we are declaring a wire. Now we instantiate a D flip-flop with instance name D, pass the variables Q, clock and reset. Next we instantiate the NOT gate. N1 is the instance name. We know that gate primitives, we should list the output variable first, which is D, and then the input, which is Q, and finally end the module. So here we have understood how the modules are instantiated and how each instance, a copy of the module, is created using instances. Finally, we write a behavioral description of the final subblock, the D flip-flop module, this code can be written in any level of abstraction. We are not going to get into the details of this code because we will be understanding each of these constructs in the later modules. So what is important here to understand is what is instantiation and what are instances, how the process of instantiation invokes the lower level subblocks in a code. So in this video lecture, we have understood what is module, how modules are declared, examples of module declaration, what is instantiation, and what are instances with an example. Thank you.